Good afternoon and welcome to our next project show for today. Team Habitat from BTU will present to you their concept of an inflatable habitat for the moon. If you have questions about the project, you're welcome to submit them on our YouTube chat. The students will be happy to address your questions after their presentation. Welcome everyone, thank you very much for joining us today, and welcome Team Habitat.
Good afternoon to everyone. I am Lubov Dimova and I am responsible for the project management, sponsoring and 3D visualization for this project. Today, together with my team, we want to present you our project for IGLUNA 2020, the Inflatable Lunar Habitat. But first, why we have decided to work exactly of this project? Probably for everybody is clear that the humanity's future is an indispensable part with the study and understanding of space. We want to explore it, but for us, the people, this is not possible without the right protection. In this sense, building a place that provides safe and comfortable living and working condition is one of the most important steps that must be taken in the building of strategy for exploring the world outside our planet. What we want to build? Of course, there are many opportunities to build a habitat for a space. But for us, it is important to make a design that is not only a vision for the future, but also can be used now, here on Earth. For this reason, we designed an inflatable habitat model that can be tested and used in terms of extreme conditions. After improving the individual elements and adjusting to the space, this model will be a building block for a small village on the moon, located in lava tubes. How we construct our habitat? The lunar habitat is an inflatable, flexible dome structure with a visible inflatable support structure. Inside is separated by an airlock and offers space for scientific experiments in extreme conditions. For us, it was very important, our habitat, to have following qualities. Less weight, that means minimize footprint for the transportation. To be flexible, measure time for assembling and disassembling. Light condition, more as 30% transparent. To be stable against mechanical impacts, and the climate regulation. Actually, the climate regulation is very important for us because we want to provide a place for experiments with plants. Who we are? We are architecture master students from BTU Cottbus, Senftenberg in Germany. You can see our supervising professor for structural design and engineering, architecture and construction, and humans factor. And here is the other part of our team. We divide our responsibility to material research, design, management and communication, sponsoring, and 3D visualization. Now I want to give the word to Maria.
Well, how did we begin? For the concept, the idea is to start thinking about several elements that it was important to follow. As first, we thought about the inflatable structure because we needed a light structure that it has also a safe system. It's easy to transport because it's we need to test this first in the Earth and also send it to the moon. Also flexible and adaptable to the structure. Well, then for the floor structure, it was important to insulate the layer and to regularize the floor and anchor the structure to make the habitat more stable. For the protective layers, it was important to develop layers either for the Earth and for the moon, and it was important to create this insulate habitat and protect it from the outside to endure the correct environment in the inside. Then we thought about an aerodynamic structure that is more stable for the wind and to keep the habitat secure and ready to endure the external variables. Also, in the moon, it was ideal to have this aerodynamic structure because the habitat that we needed to test shouldn't be changing also in the moon. And at the end, we decided to also take in consideration the climate regulations because we need a suitable environment for the people and experiments inside of the habitat. Next. Well, then for the approaches, the first idea that we had, it's had this tube that is very clean in this idea and have been surrounding the structure, but then we had some troubles when we were doing the design, and we realized that the corridor was really narrow to have experiments inside, as well as the people that was going to work inside, and also the beams that were going to be surrounding the structure were going to be below. So that's that was really a difficulty. Next, please. Then we realized that it was better to have an aerodynamic shape, because also we needed to try this on the Earth, and it's important for the habitat to be able to be stable in the Earth and to be attached. Also, the beams, when you inflate the beams, the beams are mostly rounded, so that's why we decided to actually make this structure. Next. Then the aerodynamic shape version, but thinking about the Earth, we also add this outside shell that it was going to be anchored to the floor and try to stabilize this habitat, and then also anchoring this to the frame that we were going to have, and also thinking about the climate technical system. Next. Well, what is our overall product supposed to do? Well, it was important that the inflatable habitat must provide safe and comfortable living working conditions for humans, plants in extreme environment conditions. It should be easy to transport, assemble, and disassemble, an ergonomic model capable of being adaptable both in the Earth and in the Moon, whether it's alone or part of a set, protection against external circumstances, and stability. Next.
So, hello, my name is Joanna Asef. I'm gonna continue with the presentation now, and also an architecture student of the BTU in Cottbus. And yes, so the project on Earth. The habitat on Earth has some elements that will help with the stability and the performance during the testing, such as the outer structure to protect from the wind and the weather, the material of the protective layers, or the climate technical system. And now we're gonna show you for 30 seconds a short video to show you how we would build our habitat up. Welcome back. I hope you enjoyed the short video, and now you see short little illustrations of how we would build up the habitat, as you saw in the video. And we have like some parts of them, like main systems, the outer skin, the inflatable pipes, inside skin, the floor system, and the airlock system. Next, please. So the main system, again, here the main measurements. The habitat has the total length of 9.7 meters and the width of 4.2 meters, and a total highness of 3.4 meters, and if you stand inside of it, a highness of 3.08 meters. And as you can see also, the human aspect is also important for us. So on the right section, you can see that the person that is standing inside still feels comfortable. That was important for us, and have like not the feeling of being uncomfortable inside or being in a smaller room. Yes, next please. So we have here like some cross sections, how we would connect all elements together, how would the tubes would be connected together with the outer layer, then the outer layer with the ground, and then the tubes again connected to the floor. Yes, next please. So we have some project systems, like main systems. First of all, the support structure, and then the airlock system, then the higher pressure pump, also with the air conditioner, then the floor system, then the anchoring and connection, and the outer structure. Yes. So first of all, the floor and anchoring. The floor should be easy to transport and install, enough stable to bear the weight of a P02 grower hub, and that is 2 times 320 kilograms heavy, and the P03 swag 250 kilograms heavy, and with a flat, non-slippy, and easy to clean surface. Yes. Next one is the floor and anchoring materials. So as you can see, we have the steel profile as the frame, and then the 10 stakes to make the connection to the ground, and then the steel anchorings for concrete. Yes, next please. So the inflatable tubes, the support structure is constructed of inflatable tubes. They are separated tubes and not in net connected. So when one of the tubes is damaged, the other can continue to carry the structure seamlessly. Tubes will be made of either EPFL foil or PVC fabric. The individual tubes, as well as the connections between the lower layer of the tube and the inner layer, are connected by Velcro script. Yes. So, and here again, a simulation that we did with the program Grasshopper and the plugin Caramba to show the fear of the tube they're going to impact our inflatable habitat on the Earth project. Yes. So the outer shell, as I said, the outer shell should be easy to transport and still strong, attached to the ground to provide thermal and insulation and for the habitat to be wind and weather protective and fire resistant. And in the higher corner, you can see also simulation how we figured out the outer skin to be the best version of protective for the heat. Yes. So outer shell materials, like as I said, first of all, we have the EPFE foil, then aluminum EPE from thermal insulation, then the aluminum foil membrane water insulation, and then sticker solar panels that stick outside. Yes. So now to the airlock outer door system. As you can see, we have like an airlock system with two doors. The first door is here shown, and you can enter the first one, and it's going to be closable with a zip system. And after entering the first door, next please, you have the second door that is also again working with a zip system, and where you can first enter, then change your clothes and enter the other rooms, so the different climate conditions not get confused. Okay. Climatechnical system. The climatechnical system should inflate the habitat, like with a pump, and the air conditioner should perform heating, cooling, and air circulation. Yes. Next, please. And on this illustration, you can see on the right corner how we would think of working with the air conditioner that would change control the heat and the colds inside of the habitat, and then the pump that would stay the pressure, that leaves the pressure inside the habitat, so it stays inflated. And also, as you can see, it's like separated, so the climate conditions again between the airlock system and the inner part of the habitat is like separated. And also you can see that the outer skin is protecting our habitat from the outer climate conditions and the heat. So the human aspect, as I said before, the habitat was to be tested on the Earth, has enough space inside to contain some experiments and 2 or more people in a comfortable working space, depending on the size of the experiments. That's still comfortable to stand inside, as we said. This was our Earth project habitat, and now I'm gonna let you speak, Alba, and she's gonna present the moon project of us.
So hello everyone, I'm Alba, and yeah, as Jana already said, I'm gonna explain how we imagine our project on the moon to be. So yeah, our main idea was to create a space for working and living for people on the moon, and it would be in a lava tube where it's protected from cosmic rays, meteorites, and sudden changes in temperatures, and there's also possible access to water resources in the form of ice. So the habitat we created is designed to be up to 12 people. However, it is also possible to create a bigger structure where more people can live. So yeah, first of all, we're gonna watch a short video where all the habitat is explained. So as you've seen in the video, basically the habitat is formed by two main modules surrounded by smaller ones. This is organized by function and level of privacy, what means that the function is living function or working, and then the level of privacy is the bigger modules are the common areas and the smaller ones are like more private areas. So we'll get into detail later, but for now what we want to explain is the main axes. In the plan, you can see them with arrows, the two main ones on the right bottom part, and then the emergency accesses at the end of every airlock cluster. And also just let you know that we try to avoid hallways because space is something very valuable in the moon because it's hard to create like the structures. So we avoided hallways in all ways, and we use the room dividers that you see in the middle as a storage space. Next one, please. So this is the first section we want to show you that cuts through the common module of the living space. So as you can see, there is a core in the middle. We always use the cores as space for toilet or the electric supply and the water supply. And this core doesn't go to the ceiling. So there is like another space above it where people can also like be and chill and everything. And in this space, it's thought to be like more a living area, exercise area, place to be with the other people and meet. Next one, please. In this section, you can see a cut through the other main module, the greenhouse and working area, where you also can see in the middle the core that I spoke about before. And in this case, in this core, there is a smaller toilet and a grow hub with plants, and also a technical room. And on the other side, you can see a cut through the sleeping quarters module that every sleeping quarter is for two people. And here you can see there is a bed, a table, and a storage place, private. Next one, please. So yeah, the main measures we already know from the smaller ones because they are like just the same as my colleagues explained before. But for this, we also created a bigger module to host like the common spaces that are thought to be for more people at the same time, whose height would be 4.5 meters in the middle. So it's perfect to have like the double height we were talking about before, and the and it would be like 130 square meters big. So it's okay for what we look for. Next one, please. So, okay, getting into detail, the living and common area, this would be the bigger module that was on the left, as we saw before. In the middle, you can see the core that I already talked about with two toilets, the core with the electrical and water supply, the kitchen to the left, and then the storage around it. Also, you can see a little, the one before. You can see the little arrows around it. Those are curtains that could move around it. So there is no fixed walls. And we can choose whether to have a really big open space altogether or just divide it in smaller spaces with the curtains. Next one, please. So this would be the other big module, the greenhouse one, where, as I explained before, there is a grow hub with a small toilet in the middle and a technical room and storage space around it. And then there is also tables and spots to work with the other people. Next one, please. The sleeping quarter, as I said before, it's thought to be for two people, and it has like the minimal things that a person needs to have. So yeah, next one, please. This would be the other smaller modules that we thought to be next to the working main greenhouse module, that are the scientific laboratories where people can also like work by themselves or with other people.
Hi, I'm Carlos, and you may be wondering what are the difference between the module and the Earth and the big space village community in the moon. So the main difference are specifically the subsystems in the modules. So the floor anchoring for the Earth, we need a very strong anchoring point due to the extreme weather conditions in the Mount Pilatus, because we were thinking about putting this module and testing it in the Mount Pilatus in the field campaign. So we need this very strong anchoring point because of the wind and extreme weather conditions that we have. For the moon, we don't need that much strength because we're thinking about working in the lava tubes, so we don't have wind and we don't have this gravity that we need. So we only need to keep it in the ground, and that would be pretty much it. For the airlock, we need a very strong airlock for the moon, and we don't need it so much for the Earth. Why? Because in the Earth, we have the air, like we can breathe the Earth, so we don't need this this so perfect airlock working, but we need still to keep the air pressure inside of the habitat because of the plants that we're working on and the experiments. The layers and foils for the Earth, we need several layers because also the extreme weather conditions in Mount Pilatus, we have a lot of sun, and this can be a very risky thing to be aware. So we need a lot of layers to be protecting, either absorbing or reflecting all the sun rays. In the Earth, also we're working lava tubes, so we don't have that much sun rays affecting the habitat. We only need insulation layers because we're working still in outer space, and we also have, like, it's still present. For the structure, in the Earth, we're working in one module. So this one module contains the P02 Global Hub and the P03 SWAC. And we only need the structure for these two experiments and the people that is working on them. But for the moon, we're working in a space village community. So we have to make sure that we also have this joins together with the bigger modules solved, because that would be some minor changes in the structure. Next, please. Okay, so we already consider some risk that we have, specifically in the Earth. So this risk would be the weather conditions in the same Mount Pilatus. That could be, for example, windstorm or a snowstorm. That could the effect would be that the connection is not strong enough, so the habitat would be like flown away, and that we don't want that. So the mitigation is would have several layers and separate pipes to keep the whole habitat safe. And we also have fire and electricity. For the electricity, we could cause a shortcut with one of the experiments or all the technical facilities, and that could start a fire. Also, this fire could start by itself, and to mitigate that, we would have a layer protecting for the electricity, and we also have a knife that we could, like an emergency knife, that we could also use to open the habitat and go out. This would be only in the Earth, because in the moon, of course, we can't go out like easily like that. But we also have things prepared. Next. So we consider this risk as in likelihood and severity. And the likelihood would be for all of those very low, but with a very high severity, because we're risking lives and we're risking the experiments. But the mitigation actions are very strong and they could easily work. So the likelihood, it's very, very low now, and the severity will be still high, but it's not that easily to happen. And for this financial part, we could have these sponsors not collaborating because we had this coronavirus at the beginning of the year, what still is, but now we're kind of going on it. And the risk is that these sponsors are not collaborating, but and the severity would be very high. But hopefully with this presentation and all other people can join and be interested in our project and can help us to secure this project. Next. So what are our next steps for IGLUNA 2021? Our next steps would be building this habitat. Because of the coronavirus, we couldn't build it as we thought about it at the beginning. So for the next year, we would be developing this module and building it for real. for the physical field campaign as we planned. And of course, we would be optimizing it. That means making it more light, more productive. So we could have like a cheaper version of the same project, or even better. And we're always looking for having a comfortable place for comfortable space for humans and a productive space for experiments. Next. So we want to thank Swiss Space Center, ESA, and the IGLUNA 2020 project for giving us the opportunity to work on this project and really helping us in everything that they could. And also our partners like Klimapartner, Weltreporter, Neomosel, Plastic Fantastique, to helping us hopefully to build this project, and also with the information that they gave us, and the BTU, that is our university, to making the contact and also supporting us every time. We need to special thanks to our family, friends, and everyone that supported us. And thank you for your attention, that you're listening to our project. Next. So where you can find us. We have an email that you can see here, xluna2020.habitat@gmail.com and moon@lunarhabitat.net. And we have also a website that's called lunarhabitat.net. And you can also follow us in our social media. We have a Facebook page with some incredible pictures in 360 degrees, and also in our Instagram account. Next. So we leave you with this amazing collage that we did. So you can also like feel the environment of the moon, and you can also like picture yourself and living in the space. And we're also like, why not live in not only in the moon, but other planets or in the space generally. So thank you.
Thank you very much for your very detailed and very visual presentation. We're looking forward to seeing your concept implemented in a moon village someday. And I see that our audience was also very excited and very interested in your project. We received a lot of questions. Thank you everyone for submitting the questions in our YouTube chat. Some of the questions were already answered during the presentation, but we still have a lot of interesting questions, and I see that they are related both to your future vision on the moon, but also to your current project. So maybe let's start with the future vision. So inside the habitat, you will have moon gravitation, which is 1/6 of Earth. How did you influence that? How did that influence your design?
Probably I can answer on these questions, and then Alba can help me. We have thinking about the two floors. You can see that on the corner of our project, we have the second floors where the people can go there and so make rest. Yeah, this is one part of the gravity what we're thinking.
Thank you very much. I have another question from the audience. Will the astronauts be protected from radiation when they are inside your habitat?
Actually,
so I can answer that question. Not from the radiation from themselves. Like it's on the moon in this lava tube system that is going to protect mainly our habitat and the astronauts from the radiation on the moon, and in other way the habitat in general going to protect also, but mainly the lava tubes on the moon. Yes.
Thank you very much. What design features were taken into account to ensure the human well-being aspect?
Can you repeat, please?
As it was said before, we thought about the human aspect of people. Like, we thought of what it could be for a person to live inside a place like that. So thinking about the heights and the space all over it. So yeah, I don't know, with that, we created, like, as they told, first the smaller habitats and then the bigger ones following that design.
And in both of them versions, we still have the focus on the human aspect, so that the human feel comfortable inside of it, with the size of the smaller habitat, that it's still really not feeling inside a smaller room. You have the freedom, even though there are these machines inside of them that we're going to build or have inside our Earth habitat, and the moon project habitat of us is like still also focusing on the human aspect. That's why we have this green space areas, and so you have still the feeling of being comfortable and being surrounded by something that you like and enjoy, like the nature or something that we humans need. And this is what we had in focus. Yes.
Great. So I see that indeed you considered the human well-being into the design of your habitat, but actually I have someone from the public asking you, would you also think about having pets into the habitat in the future on the moon?
I'm not really sure if it's gonna work that well. They were trying to send some pets to the moon. Could work. I'm not 100% sure, but why not?
Why not? So sure. Another question, guessing at some point it will be needed to clean the habitat because of the dust from the moon. Will the astronauts do that with your design?
We haven't really thinking about this part, because we was concentrate of the Earth prototype, but yes, possibly. Yeah, we should thinking about it.
Thank you. And still on the moon topic, will you be able to build everything with the equipment directly on the moon, or would you have to bring everything from Earth to the moon and build it there?
Actually, we need to bring this to the moon. So this is the idea from the inflatable structure. So we need not so much place in the rocket, but we need to take this from the Earth, and it's not possible from there to use technology.
And that's also the reason why we use the ETFE foil, because it's like a different type of plastic. So you can transport it in a smaller size, and you can inflate it, and then you have this shape, and you can use with the air and pressure that it stays in shape, and you can get sizes that are like huge, and where you win from a smaller size to bigger size. So yes, the reason why we choose that material. But we need things to build this up at the moon, yes.
So you mentioned bringing with the rocket. I think it also answers one of the further questions that we had. The question was, with its current status, would your system fit into the rocket, or is it a bit too bulky at the moment? I suppose you have already answered that question as well. Did you consider your inflatable habitat on the lunar surface, but surrounded, covered by lunar regolith 3D print material, with the inflatable habitat providing support during 3D print?
Yes, actually, this is a good idea to have the surrounding layers from regolith, but we have one time with the lava tubes. Probably a second time will not will be good idea.
I have another question from the audience as well. Have you considered micrometeorite impacts and the potential regolith debris that could be thrown at the habitat?
Yes, we have like a different type of we have a different type of layers. So one of them is also protecting of the micro things. And in general, as we said, it's going to be built and inflated inside of one of the lava tubes in the moon. So there's a lower risk of getting hit by micro things that are flying around in this space. And in general, also our tube system is like also as a construction stabilizing system. So if something's going to fall on it or something, it's going to protect the habitat in general, the inflated one. Yes.
Thank you very much. That was a very interesting discussion about your future vision. Now back to the Earth and to the current project. I have a question. What gas do you use to inflate the tubes of your habitat?
What?
What gas do you use to inflate the tubes of your habitat?
we were like actually thinking of, on the Earth project, it was planned to use, let's say, just air. We know that on the moon it's like going to be like a little bit more difficult, but there are like still scientists actually working on that. Like I heard of some machines to get some from the water or something, some oxygen, so to inflate things at the moon, on the moon. So we have to wait of like some cooperation with other scientists, but it's just planned with air actually.
Thank you very much for your answer. And I see someone from the public is also really interested. Can students from other universities, and how can they get involved into your project?
Actually, they can. They can write us in the email and or Facebook, and we will speak together. And for the next year, it's very big pleasure to work with other university too.
Yeah, we welcome everyone.
Thank you very much. That was a very interesting Q&A session. We still have some time in case you would like to say something to the public, some last thoughts to share. It's your chance. If not, then I would like to conclude this session. Thank you very much, Team Habitat, for your very nice presentation. Thanks everyone for submitting the questions. That was a very interesting discussion to get to know your project a little bit better. And thank you for watching us. Please stay tuned. There will be a talk from Swiss astronaut Claude Nicollier in about an hour from now, so make sure not to miss it. Thank you very much. Have a nice day and goodbye.
Good afternoon, everyone. It's really exciting today because we have Claude Nicollier, our Swiss astronaut and professor at EPFL Lausanne. Claude flew actually in 4 space shuttle missions from 1992 to 1999. He took part in 2 servicing missions to Hubble Space Telescope. One was called STS-61 in 1993, and the other one STS-103 in 1999. And today he is going to present 30 years of Hubble because actually this year we're celebrating Hubble's 30th anniversary. Please submit your questions and comments through that chat in YouTube, and Claude will be answering after his presentation. Welcome, Claude, and thank you very much for your time and your support to the IGLUNA Virtual Field campaign. We look forward to your talk.
Okay, good afternoon to everyone. Participants in the IGLUNA project and the whole project team. And it's a great pleasure and a privilege for me to be here to talk about Hubble 30 years and about my privileged experience of having gone to Hubble on 2 occasions to do repair work there. I would like to congratulate all of the participants in this IGLUNA 2020 project. I've been following some of the project, and I'm really impressed that we have real explorers and people who are going the right direction to continue space exploration. And I would like to take again the words that were used at the introduction by Jan Werner, curiosity. You show curiosity, an enormous amount of talent to move things forward in space exploration. A few words about myself. I've been an ESA, European Space Agency astronaut for nearly 40 years. I was selected in the very first selection in 1978. So I'm an astronaut of the past. I'm a dinosaur astronaut. In a week from now, you'll hear Alexander Gerst, who was selected in 2009, who flew on the International Space Station. But I flew in the past. But I had a really superb and very privileged career as an astronaut, especially visiting Hubble on 2 occasions. I was assigned to the Johnson Space Center in 1980, and I stayed there for 25 years. And as mentioned already, I flew 4 missions, including 2 missions to the Hubble Space Telescope. I'm retired now as an astronaut, but I'm still teaching at EPFL, Swiss Federal Institute of Technology in Lausanne, in space technology, and sharing my experience with students. This is the Hubble as it is now, with the small solar arrays. When we visited it for the first time in 1993, it had the large British aerospace solar arrays that had been replaced in 2002. But apart from that, Hubble looks very much like it now, and when we visited it in 1993, it looked very similar, apart from the solar arrays as mentioned. Hubble is a real treasure in the sky, treasure for astronomers, treasure for humanity. For astronomers, because it brings us so much data, very high resolution data about relatively close by objects in the solar system, objects in our galaxy, and extragalactic objects until very large distances, billions, I say again, billions of light years away. A real treasure in the sky. And for me, my original training was as an astrophysicist who became an astronaut. It was a huge privilege to go and visit Hubble on 2 occasions, especially the very first servicing mission in 1993 that had as a main objective to fix the optical problem that we had for the first 3.5 years of operation. Okay, 30 years Hubble, it means that it all started 30 years or a little more than 30 years ago on the 24th of April, 1990. It was the launch of the Hubble Space Telescope with the Space Shuttle from Kennedy Space Center, Florida. And I have a short video that will show the liftoff of Discovery on that mission, STS-31, the 31st shuttle mission. and you'll see it going up and then going through clouds, and it will end shortly before solid rocket booster separation 2 minutes after liftoff. But 30 years since the launch of Hubble on shuttle Discovery from Kennedy Space Center. And I must say, I'm always impressed when I see these pictures of a shuttle launch, because when you think that you have inside the payload bay of Discovery, the very noble, precise, complex scientific instrument that will eventually point to celestial object with an accuracy of 7,000 of an arc second. And it goes up in this machine with a lot of vibration and shaking. It's quite amazing. And it was a really big engineering challenge to bring that very precise scientific instrument to orbit in the space shuttle. Okay, let's go with the launch. Okay, now we are on orbit. After a while, the altitude of the orbit was 600 kilometers, so quite a high orbit for the space shuttle. Inclination 28.5 degrees, which is the latitude of the launch site, Kennedy Space Center. And this is a magnificent picture of the release of Hubble to orbit. So it's a completely different environment from launch. Launch, you have these huge flame, you have the vibration, the shaking. And then when you are in space, it's completely silent. You have a completely black sky, you see it in the background. And the telescope was filling the whole volume of the payload bay. It's been grappled with a robot arm. Taken out of the payload bay, the solar rays have been deployed, oriented to the sun to charge the batteries. And now we just had release of Hubble on its orbit at 600 kilometers altitude. So in a way, it's formation flying now at 28,000 kilometers an hour. A few days later, the cover that you see on covering the optical part of the telescope was opened, and the pictures were taken of the first stars. And we had, in fact, a big problem I'll talk about in a minute. But let me show you here the optical configuration of the telescope. It's pretty much like a telescope that we have on the ground, except that it is in space. It doesn't have an equatorial mount or alt-azimuthal mount. You had the radiation from the celestial object coming from the left, hitting the primary mirror here, which is a concave mirror, hyperbolic shape. It's a so-called Ricci-Chrétien configuration. Then it changes the parallel beam to a converging beam to a secondary mirror, also hyperboloid. Another reflection, then you have the focus formed in the back of the primary mirror. And observed with a variety of scientific instruments. You have here the list of the so-called axial instruments: space telescope, infrared spectrometer, the cosmic origin spectrograph, the advanced camera for surveys, near infrared camera, and multi-object spectrometer. So 4 scientific instruments in axial position. And you have also equipment in so-called radial position, 5 guidance sensors, 3 of them, and the wide field camera number 3. We started with 1, then 2, now we have 3. This is the configuration we have right now. Now at the periphery of the telescope, you have equipment bay like computers and gyroscopes and equipment that can be exchanged, but that's not inside the telescope, it's at the periphery. Now we have a baffle to prevent stray light on the telescope. So this is the inner configuration of the telescope. And when an attempt was made to get the first pictures of stars, that's what was expected. Of course, a star is basically a point in the sky. With an instrument like this one, you don't see the size of the star itself. It's like a point. And normally with the wave character of light, you should have a so-called airy pattern with little wavelets. And we were expecting a picture like this on the CCD sensor at the focus of the telescope. That's what we had, a completely spread picture of an individual star. Obviously, there was an optical problem, and the cause was the 2.4 meter diameter primary mirror was shaped slightly too flat because of an error in the configuration of the reference to be used for the shaping of the mirror. So, well, that was a big problem, and it was planned anyway to have servicing missions, and these are all the servicing missions that were performed from 1993, the first one, until 2009, the last one. And obviously, the first one, December 93, had as a main objective to fix the optical problem. We could not exchange the primary mirror, but we could install an optical corrector to, on one hand, correct the faulty shape of the primary mirror for the axial instruments, and we had to change also the wide field camera. So there were two actions that had to be done to fix the optical problem. As you see, the very last one was in May 2009, which was just 2 years before the shuttle was retired. And the telescope is still working fine after that last servicing mission. But if there's any problem now with it, we cannot go back because we need the shuttle for servicing the telescope. Okay, now this is a crew that was selected for the very first servicing mission in December 93, so 3.5 years after the launch of the telescope to orbit, as I described. And these were very privileged people, and I'm here as one of the very privileged crew members for this mission. Dick Cabby, the commander, Jeff Hoffman, Tom Akers, Ken Bowersox, the co-pilot, Katie Thornton, Story Musgrave, and myself, in cooperation between the United States, NASA, and the European Space Agency. This is the logo of the mission. In fact, I was the designer of that logo. We have the astronaut symbol with the star, the 3 rays down at the orbit. And I try to combine the astronaut symbol with the light from the star being intercepted by the primary mirror, reflected to the secondary mirror. And finally, we have the picture here on Earth, which gives us information about that star for us, people on planet Earth. That was a symbol of the optical configuration of the telescope and the astronaut symbol. And here you see objects that were going to be studied, like planets and stars in our galaxy and extraterrestrial objects, with the names of all of the crew members. Now, of course, it had never been done to do major repair work on a complex scientific instrument in the space environment. And we did a lot of work in the virtual reality lab at the Johnson Space Center. You see Jeff Hoffman in virtual reality. This is virtual reality of the early 90s, so it's not as fancy as we have it now. And I'm here operating virtually the robot arm to bring Jeff Hoffman to a proper position to do some repair work. Dick Cabby, the commander, Ken Bowersox, the co-pilot, and Katie Thornton. A lot of work in the virtual reality lab as a preparation before going in the water and practicing the exchange of a scientific instrument and also other features that we exchange. This is a practice of the replacement of the wide field and planetary camera. We had the number 1 on board. We replaced it with the wide field planetary camera number 2 with a corrective optics. And this is the wide field planetary camera number 2 during the mission itself. And you see the great similarity between the training unit and the real unit. We had excellent training methods with very high fidelity equipment in order to avoid surprises. When you work with something that is very similar to what you will find up there, then you avoid surprises. You are more likely to be successful. Now, the reason we trained in the water was, of course, to recreate pretty much the weightless condition that we have in space. We trained for 1 year, and the night of the 1st or the 2nd of December 1993, I remember that very well. It's a very special moment when the little bus takes us from the crew quarters at Kennedy Space Center, where we had spent the last night, to the launch site here in the middle of the night at 1:30 a.m., about 3 hours before liftoff. I can tell you this is a very special moment. You open the door of that little bus and you see your spaceship with a cargo bay filled with equipment to be replaced on Hubble, with a nose pointed upwards. And in 3 hours you're going to go fix Hubble. And the guys who are with you, they tell you, guys, go fix Hubble now. Okay, we'll do our best. We go up with an elevator, then on this bridge to the white room where we do the last preparation before sitting in the cockpits with the feet up. And at 4:26 in the morning, we had the liftoff of our spaceship with destination Hubble Space Telescope. Now the following and the rendezvous with Hubble took 48 hours. At that time, that was a duration, standard duration for a rendezvous. And here we are, formation flying with Hubble, 28,000 kilometers an hour, approaching slowly the telescope. I was responsible for the operation of the robot arm, which you see on the lower right, to grapple Hubble and install it in the payload bay of the shuttle. You see here the installation complete, the small platform in the back of the payload bay. This is Hubble with the old solar arrays, which, as you see, are not in very good shape. We had new ones folded in the payload bay. That was the objective of the last spacewalk out of 5 that were planned for that mission. We are 600 kilometers altitude. You see Madagascar here, the island of Madagascar on the upper left. Now, we had 5 spacewalks planned and rehearsed and trained extensively on the ground in the virtual reality lab on one hand and in the water. As I mentioned, I was a robot arm operator. You see me on the upper left. And optical fix number 1 was a replacement of the wide field planetary camera from number 1 to number 2. And on the right-hand side, you see Tom Akers and Katie Thornton. Katie Thornton at the end of the robot arm, as you see here, before installation of COSTAR, corrective optics space telescope axle replacement, to correct the faulty shape of the primary mirror for the axle instrument in the bottom of the telescope. That was the most important spacewalk of that mission. We had 3 more, and then the last one, the number 5, had as an objective to exchange the solar rays. As you saw, they were not in very good shape on that picture when we installed the telescope in the payload bay. And this is after exchange of the solar ray. These are the new solar rays, but they are not yet unrolled. This is a beautiful picture. This is Story Musgrave at the end of the robot arm with the tools in front of him. And you have Jeff Hoffman in the payload bay. We are 600 kilometers above Australia with Antarctica in the background and the black sky. Such a beautiful workspace. For me, it brings back amazing memories. And when I see this picture, there's a lot of emotion in me. This is amazing. What a superb work environment and a very meaningful mission at the same time. Now, this is the happy crew. We had done everything so far that was expected of us. You see the telescope still attached to us in the back of the payload bay with the new solar arrays. So this is a group picture of a happy crew because we had had success on this mission. What we didn't know at that point was whether the optical correction was satisfactory or not. And we got to know that a few weeks later, but I would like to introduce you our lead flight director, Milt Heflin. He was directing the whole team in the Mission Control Center. And I show a picture of Milt for you to understand that this was not our mission, not only our mission, the 7 crew members on board. It was a mission of a lot of people. And the people on the ground were under the lead of Milt Heflin, who was a very, very talented and extremely capable flight director. All the flight directors that I had the opportunity to work with at the Johnson Space Center Houston are superb people. Milt Heflin, we can thank him for the success of this mission. The wise man, I put here the wise man. We on board our spaceship were like cowboys doing our work, but the wise man was Milt Heflin. And we had a lot of support by the Goddard Space Flight Center, amazingly high quality support by Goddard. responsible within NASA for the Hubble Space Telescope operation. Now we got to know a few weeks later, that was in the beginning of 1994. This is Barbara Mikulski showing at the Congress session a picture of a Messier 100 galaxy before the optical correction and after the optical correction. Picture taken with a wide field and planetary camera. Number 1 here before our servicing mission, and the number 2 here that we had exchanged. Success. Not only during the mission itself, we got to know that everything had worked, but the optical correction was perfect also. This is a huge satisfaction for us and the whole team. Now, we had in 1994 and 95 a few classical pictures of Hubble that showed the extreme performance of the telescope after the servicing mission. And I remember in the middle of 1994, we had an impact of pieces of comet Shoemaker-Levy on the surface of Jupiter. And see here one of the scars, one of the biggest chunk of the nucleus of that comet that impacted the atmosphere of Jupiter. That was really an amazing result. And then we had this famous picture of the pillars of creation, Messier 16, the Eagle Nebula, a star-forming region in our galaxy. And a very interesting picture of a protoplanetary disks in the Orion Nebula. These are stars in the making, globules of interstellar matter getting denser and denser, warmer and warmer, and finally hot in the center. Eventually, you have a temperature that will trigger thermonuclear reaction like what happened to the center of the sun, and they will become real stars. So these are 3 pictures that I remember very well, and that was a huge reward for the whole Hubble team, including the 7 crew members who were on this mission. Hubble was becoming now an extremely, extremely productive scientific instrument. Now, one picture that was not in 1994, it was 1995. We had the first so-called deep field. The telescope was pointed during 10 days in the same small region of the sky in the constellation Big Dipper, Ursa Major. It's a very small window. It has the shape of L plus another square here. That was due to the optical configuration of the wide field planetary number 2 that was used to take this picture. This is about 2 arc minutes by 2 arc minutes. So 1/15th of the diameter of the full moon. And basically that was a region of the sky where there was nothing, it was black. And after 10 days of exposure, you see here on this very small window in the sky, thousands of galaxies. And this is so impressive. And this is the first of the several deep fields that were taken with Hubble. And for me, I remember in 1995, a little more than 1 year after our mission, it was a huge reward to see the extreme performance of the telescope to look at the very, very far away universe. The faintest galaxies here have a distance of several billion of light years. We see them as they were billions of years in the past. So this is a look in the depth of the universe, also in the past of the universe. I was, again, privileged to take part in another servicing mission. We had another one in 1997, which is servicing mission 2, which mainly exchanged scientific instruments to make of the telescope a better, more capable scientific instrument on orbit. And the third mission, mission 3A, that I was part of, and here you see me training as one of the potential spacewalkers for this mission in the neutral buoyancy lab at the Johnson Space Center, Houston. You see even a higher fidelity model of the telescope than we had used for training for our first servicing mission. We open here the doors in the bottom of the telescope to get access to gyroscope. We had a problem with gyroscope. Out of 6 rate sensor units gyroscope, we had 4 that had failed, and 2 were not enough to allow the telescope to be pointed precisely to celestial targets. So we had to exchange all 6 gyroscope. We had to change also one of the fine guidance sensors and the main computer of Hubble. So that's typically what we did for a long time, Typically, the session in the water lasted 6 hours, and we had many, many of them to train for spacewalk. Spacewalks are extensively trained. It's not improvisation. You don't go out with your spacesuit and your tools and think, what am I going to do? You know exactly what you are going to do. And it's very extensive and very tiring training, and it's a lot of focus and concentration. Here we are, December 1999, servicing mission 3A, main objective to exchange the gyroscopes, plus the other items I mentioned before. And this is a preparation for spacewalk number 2. This is my spacesuit. Each spacesuit is identified with a marker on the leg and on the side of the life support system. This was mine. This was Mike Fold, my colleague, on this second spacewalk of the mission. You see here inside the cabin, we have all of the tool and equipment that we have to take for a specific spacewalk. Preparation for spacewalk number 2. And here we are, servicing mission 3A, EVA number 2, fine guidance sensor number 2 exchange. This is the old fire guidance sensor that had failed. And I'm at the end of the robot arm, inserting in the telescope the new fine guidance sensor. And that is Mike Fold, my colleague. He's doing the ascent of the north face of Hubble to join me. We are again over Australia, 600 kilometers. The robot arm was operated by Jean-François Clairvoy, another European Space Agency astronaut. So we were 2 Europeans on board this third servicing mission of Hubble. And a little later, we changed our role with Mike Fold. I became the so-called free floater. Mike Fold became the EV number 1 at the end of the robot arm, being brought to his place of work by the robot arm operator. And we are doing brain surgery here. We're exchanging the main computer of Hubble. You see I have my safety tether attached. For all of you who will be going spacewalking in the future, I'm sure some of you will, never forget to attach your safety tether. Because if you detach from the structure, here I'm holding the door, avionic bay door number 1 on Hubble, but if I let the door go and I'm moving away from the shuttle and the telescope and I'm not attached, it's really a bad day. So you have to avoid this. You always have to attach your safety tether. That's a recommendation. And work slowly also. If you work too fast, you lose control. Work very slowly, attach your safety tether. You're going to be okay, and train a lot. It was a busy but successful and happy day in space. This spacewalk number 2 lasted 8 hours and 10 minutes. We had a number of problems for the insertion of the fine guidance sensor number 2, but eventually we were successful, happy. Here, I have my feet on the payload bay of the shuttle and my head down to the Earth. You see the reflection of the Earth on the visor of my helmet. We were 8.5 hours outside, so we went 5 times around the Earth. It's day, night, day, night, day, night, day, night. And you see here the floodlight that allowed the illumination of the place of work during the short half-an-hour orbital night. Nice picture of the telescope that has been grappled after the 3 spacewalks accomplished, grappled with the robot arm taken out of that platform at the end of the payload bay. Beautiful picture. You see the sun just peeping just from the side of the telescope. You have a crescent of the Earth becoming thinner and thinner as the sun is coming down. This is just before sunset, about 2 minutes before sunset. Then the crescent becomes thinner and thinner. Then it disappears at sunset and you have half an hour of night. That's a picture that I love also. This is at about the same time. You have under us a so-called terminator, the limit between day and night on the surface of the Earth. And the sun was still illuminating us, illuminating the wings, and the reflection of the sunlight on the wing was illuminating the bottom of the telescope. So we have this very high contrast picture. Again, it brings me incredible memories and emotions. That was so beautiful. Okay, here we released Hubble. That was on Christmas Day, 1999, 25th of December, 1999. And we took an appropriate crew picture on a Christmas Day. We had Santa Claus hats in one of the drawers in the cabin, and we took this special crew picture, Hubble, servicing mission 3A, with success, 7 crew members. Now, Hubble was serviced again on in 2002, the second part of servicing mission 3, the so-called 3B mission. And then finally, we had the servicing mission 4 in May 2009. And this is a Hubble post-servicing mission number 4, where the crew installed a new solar arrays, where they were already installed in 2002 on servicing mission 3B. But now we have the new solar arrays, which are still on the telescope right now. And the crew installed also a docking port here in the bottom of the telescope, because the telescope still works fine, and it will hopefully still for a few years. But at some point, we'll have to bring it down to Earth in a controlled manner. We don't want to let it come down by itself. We don't know where. So the idea is to bring a robot to dock on these docking ports and do a controlled deorbit of the telescope, probably with a splashdown in the Pacific Ocean in, I don't know, 10, 15 years from now. We're not in a big hurry, but the telescope is slowly coming down. Okay, now I got to show you some results taken by Hubble. I go quickly through this to where I kneel at the end, but I want to show you here a beautiful picture that was released on the occasion of 30 years Hubble. It was on the 24th of April this year. It's a cloud of gas and dust in the Large Magellanic Cloud, about 160,000 light years away. A beautiful picture. Let's go with the video. Okay, now you had a great result from Hubble in our galaxy, or let's say close to our galaxy, because the Large and Small Magellanic Cloud are satellites of our galaxy. But of course, we use the telescope a lot. We used in the past and still now to look at objects outside of our galaxy, typically other galaxies. Here you have some nice pictures of outer galaxies. The one on the left is pretty much like our galaxy if we could see it from outside. And on the right, you have interaction of two galaxies with distortion of the spiral arms due to the proximity and gravitation. And now I'll show you another video that has been released recently. The whole video is not all taken from Hubble, but you have a zoom on the Andromeda galaxy, which beyond the two Magellanic Clouds is relatively close to us, about 2.5 million light years away. And you'll see this zoom that has been recreated, and only the very last picture of the Andromeda galaxy, you will see a picture taken by Hubble with individual stars of the Andromeda galaxy. Normal stars, not the supergiant, but normal stars. Okay, let's go with that zoom. Okay, you saw on this last video at the end, you have all these little grains of sand. These are individual stars of the Andromeda galaxy, 2.5 million light years away. Now, this picture is really a symbol of the legacy of Hubble. I'm not going to go through all the detail, but you see a few objects that are stars in the foreground in our galaxy. Then you see a number of a spiral galaxy. You can recognize the spiral character of some of the galaxies, or elliptical galaxies. And then beyond that, you have just galaxies everywhere. Here you have the picture of a galaxy that has been distorted by gravitational lens effect. So this is typically the kind of beautiful picture, an extremely useful picture for understanding the faraway universe taken by Hubble and still taken now by Hubble because still working fine. Now, why so much success in Hubble servicing? We had these 5 servicing missions that were very complex and we had total success on all of them. Very briefly, Hubble had always been a huge source of inspiration, goals and priorities on every related shuttle mission, whether it was the deployment of Hubble in April 1990 and all the servicing mission until 2009. Very strict operational discipline in space and on the ground. This is typical for all space flight, but it was especially the case for Hubble. Thorough and very high quality crew training in realistic environment, extensive practice for handling malfunctions. I mentioned that already. And teamwork at all levels, very close collaboration between the mission control center under the lead of the lead flight director and the flight crew. Now the successor to Hubble, I say successor quote unquote, because it will be an infrared telescope, quite a bit larger size of the primary mirror than Hubble. You have here the 2.4 meter diameter primary mirror of Hubble, and this is the primary mirror of the James Webb Space Telescope, 6.5 meter diameter segmented mirror. It will be launched, if everything goes well, next year with Ariane 5 from Kourou, French Guiana. It's cooperation between NASA, the European Space Agency, and the Canadian Space Agency will be put on the L2 Lagrange point of the Sun-Earth system, 1.5 million kilometers away from the Earth in the anti-sun direction, not serviceable. I hope it will work fine, but that's a telescope after all the parts have been deployed. And we expect a lot of results, study of the faraway universe with the James Webb and also study of exoplanets. But Hubble is still working fine now. Of course, it will only have a few years to live because of either batteries or gyroscope or other component at some point will fail and then we'll lose it. But what an incredible achievement this was. And the human component of Hubble was also very, very present, including the big mistake at the beginning, but the repair, the fixing. This is it's a program with a lot of human component, which is extremely rich and extremely valuable. And by the way, all the Hubble treasures you can find on this website, www.hubblesite.org. Thanks for your attention. It was a pleasure to share the Hubble treasures.
Thank you very much, Claude. I'm simply wow. This was a fantastic presentation. The picture is amazing, and it's also really nice to hear from your experience. It makes me also, I was imagining myself in space as you described your experience. I was feeling it too, getting excited. It's really inspiring. Thank you very much. We really like to have this first hands-on experience from your missions in Hubble servicing. So it's really nice. We had a lot of interaction in the chat, and I was just checking quickly. Some are about your experience in space, some are about Hubble. So let's start first with the ones related to Hubble. And the first one goes like this. Given your experience with Hubble, what are your thoughts on the new James Webb Telescope? Do you think its expected launch next March will be further delayed?
I think it has already been announced that it will be delayed. It's not going to be next March. It's going to be sometime in 2021, we hope, but it's not going to be in March. It's a very complex instrument, and it will be extraordinary in its performance, but very complex. And of course, there's a lot of new ideas. This whole tent that you saw is supposed to protect the telescope against the radiation from the sun, the Earth, and the Moon. So it's only we'll see the deep space, the deep black space, and the galaxies far away. And the temperature of the telescope will be about 40 K by itself. Of course, the instrument will be cooled even more, but the telescope will be very cold. But technically speaking, it is a very complex instrument. That's the reason why it was delayed. Quite expensive also, but shared between these 3 space agencies and a number of nations. I think it's going to be a success, but it will be delayed a little bit beyond March next year.
Okay, we'll stay tuned to see when it actually is launched. Now about specifically Hubble, they were asking what is the best image for you that was taken by Hubble?
Oh, there's so
Your
many great
favorite
pictures.
image.
Well, I have to say, but of course, this is something that I've really experienced. The first deep field that I've been showing is the one that touches me most, because we realized at that point, that was again in middle of 1995, a little more than a year after the first servicing mission, using the wide field planetary camera number 2 that we had installed. And we realized at that point that the telescope has such an amazing capability for looking at the faraway universe and faraway object. This is the one that touches me most. There were a lot of other deep field taken by Hubble, the deep field south. All the deep field are taken in the region of the celestial North Pole or South Pole, because these regions are always visible from the orbit of Hubble. If you have an object close to the celestial equator, it will be periodically occulted by the Earth, and you need to stop the scientific instrument. You waste exposure time in a way. But there were several deep fields, and they are all amazing. But the very first one is touching me most.
Yes, I understand that. That's clear. To follow up on this question, would be what is the most amazing thing we learned thanks to Hubble?
Oh, there's so many. It's mainly about composition of the faraway universe and the formation of the early galaxies, and the proof of the presence of a black hole at the center of galaxies. So extraterrestrial astrophysics and cosmology, that's one thing. And also a lot of pictures of the galaxy distorted by the gravitational lens. A lot of pictures taken by Hubble in that area. And that's one thing. Extragalactic astrophysics, and in our galaxy, it's star formation. We have so many pictures where we see the transition from gas globules or gas clouds all the way to stars. And we understand much better the formation of stars, including the formation of a planetary system around stars. When I show this picture of the protoplanetary disk around protostar in the Orion Nebula, we have a dark area around these protostars that will be future planetary system. Of course, we've observed in the meanwhile a lot of exoplanets. So in a way, we make the link between the clouds of gas and the formation of planets around many stars. A great fraction of stars are surrounded by planets now.
Good, thank you. Going to the future, if actually you could design the next space telescope, what would it do, and where in space would it be flying to?
Well, what we need now is really a wide field instrument. And in fact, there is such a program that is in preparation at NASA, because the problem with as well Hubble, and to a certain degree the James Webb, is that it looks at the very, very small region of the sky. So you learn a lot about a specific object which is small. We want to have wide angle views of the sky from space, including in the region of the wavelength that are not accessible from Earth, which mean the far infrared and the ultraviolet and the shorter wavelength.
Okay, so we'll keep tuned for that as well. Now, coming to your experience as an astronaut, actually, many viewers had questions about that. One was saying, well, you mentioned that you prepared very extensively for the missions, and actually I was very excited to see that you also use virtual reality, because some of our student teams in the IGLUNA program are focusing exactly on this, on developing virtual reality in order to train for future missions. So they are asking, how long before the missions did you have to train?
Okay, good question. Now, we had a so-called basic and advanced training on the space shuttle, which was taking about 3 years. And after these 3 years, you are transitioning from an astronaut candidate to an astronaut. During the first years of training, you are not really an astronaut, you are a candidate only. If you graduate to become an astronaut, then you are eligible to be assigned to a given mission for the shuttle with 6 other crew members, because there were 7 crew members total on nearly every shuttle mission. Sometimes 6, once we were 8. But anyway, at some point, a crew is selected for a given mission roughly 1 to 1.5 years before the mission. I'm talking here about shuttle mission. The International Space Station is somewhat different, although they train in in different locations. They train in Houston, they train in Canada, they train in Japan, they train in Europe. For Hubble, we were training only at the Johnson Space Center, except short training period at the Marshall Space Flight Center and also at Goddard Space Flight Center. But basically, the training for a shuttle mission was typically 1 year to a year and a half, very intensive training. And again, we train not only for the nominal mission, as we hope will happen, but to cover a number of failure cases and malfunctions and sometimes disasters even.
Yes, I think that's really needed also to be prepared and stay calm when you're up in space to be ready just in case. That's really interesting. Actually, our viewers are also curious about becoming an astronaut, and they ask, what would somebody have to study to become an astronaut? What tips would you have for them?
Now, I know the case of NASA and the European Space Agency, which are very similar. They ask for a degree in engineering or science or medicine, and 3 years of experience, of work experience after the university degree, which is normally a master's. If you go do a PhD, then some of the years used for the PhD count partly, at least, for the 3 years experience after obtaining the master's degree in science or engineering or medicine. Now, you need to be in pretty good health. You don't need to be an athlete, but you need to be in pretty good health. And mentally stable, and this is measured because they have all kind of machine to measure your mental stability. And you have a number of interviews during the selection, and they ask you a lot of tough questions, and that's their way to check whether you are mentally able to cope with the stress of the interviews or not. Now, these are the main areas: university degree, 3 years experience, good health, and mental stability. And if you have the opportunity to do some activity that involves risk management, whether it's mountain climbing or parachute jumping or aviation, or like aerobatics and instrument rating, these are all things that go in the right direction, because in a spaceship, when things go wrong, it can be pretty stressful, and you need to stay calm, use procedures, talk to the ground. And you learn a lot of these when you practice these activities like aviation or mountain climbing.
Sounds very challenging, but yes, I think it's something very inspiring as well. We have actually, because you're our only Swiss astronaut at the moment, someone asked, will there be another Swiss astronaut in the near future?
There could be thousands of Swiss astronauts now. I think the motivation and the talent in Switzerland is there, and in fact, it is in all countries. But in our small country of about 8 million people, there are a lot who could be astronauts, who have all the qualifications. The problem is that you have to go as a Swiss citizen through the European Space Agency. Switzerland is one of the members of ESA, one of the 22 members. And if you want to become an astronaut and you are a Swiss citizen, you should not go to NASA or Roscosmos in Russia, which are great agencies, but they take their own people. So the Swiss, you have to go through ESA. And ESA selections are not very frequent. I was selected in the one in 1978. The next one was in 1992, and the third one in 2009. So every roughly 15 years, you have a selection. There should be one pretty soon, in a few years from now, maybe next year, maybe the year after next. And all of the Swiss and every male and female citizen of all of these member states of ESA should, if they are motivated, they should prepare now already. The idea is to be broad. You have to be an expert in your area of research, but you have to be open to other disciplines also. Because in the interview, they ask you a lot of questions about disciplines that are not your discipline, but other disciplines, to verify your interest and knowledge in a wide area of knowledge in science and engineering. And you can be a medical doctor as a job, but you have to become also a little bit of an engineer and scientist. If you are a scientist, you need to become a little bit of an engineer and a medical doctor. And if you have a pilot rating in addition, this is always helpful, because you are accustomed in airplane to handle the situation, sometimes make decisions, including when there are problems occurring. And in a spaceship, they occur not all the time, but they occur sometimes. Need to be ready.
Great advice. Yes, that's good to do. And I do know a couple of people training for this, so I look forward to seeing them maybe selected in the near future.
But again, I have to say again, for the Swiss, Switzerland is a small country. It's not in front of all the other countries at ESA. It's one of several small countries. But for the students, men or women, students in Switzerland who have the motivation, who want to get there, they can get there. There's absolutely no doubt about that. And the reason I don't have a successor until now is that there are so few positions available. But the Swiss have their chance. They just have to be motivated and work hard.
Actually, to follow up, someone was asking, would you go to space again?
I said I'm a dinosaur astronaut. They would not take me anymore because I'm too old. But I think I would be able physically and mentally to take it. But there are so many younger people who are so capable, including Alexander Gerst, who will talk to us next Sunday in 1 week from now. And the last class of ESA astronaut, there were 6 people. In fact, the 7th was added. Matthias Maurer was added, so 7 total. They're very talented people. I'm so happy to have flown magnificent missions. And for me, the memory of this mission is satisfying me fully. I would love to go back, but I will not go back. And I'm so happy with what I was able to experience. Now I let the younger astronauts take care of the future missions, including the one who are listening to us and looking at the pictures. I'm sure that among the IGLUNA campaign 2020, there are a few of them who will become astronauts. I'm convinced of that.
That's nice of you. Thank you very much. Maybe just to correct there, Alexander is talking on Thursday, not Sunday. So July 16th.
Thursday. Okay, sorry.
Perfect. Yes, so that people are watching as well, because you are also speaking again that day. So it's really exciting to have you again then speaking about moon exploration. And today we're doing Hubble and actually your experience in space. We have a couple more questions before our time's up. One was asking, what was the best thing you experienced in space from all of your missions?
Okay, I got to tell you. 23rd of December 1999, on my last mission, I was spacewalking EVA number 2 with Mike Foale. And the first time with my gloved hand, I touched Hubble. It was a magic moment. And this was probably the best moment I had in my whole astronaut life, touching Hubble. Not with my hand like here, but with my gloved hands.
Yes, well.
Hubble meant so much for me. It means so much now that being able to touch it. Of course, later I worked on it with tools, but for the first time when I touched it, there was something very special that went through me. And it's still with me here.
We can feel it actually just by hearing you talk about it. That's really nice. And talking about your feelings, what were you feeling when you were in space? Was it excitement, scared, and was it different in every mission?
Well, that's good. The very first mission, of course, to discover this completely new environment, which is somewhat intimidating. You know, it's not, people think, well, it must be great from the beginning to the end. No, the first moment after main engine cutoff, the first time you experience weightlessness, when you are in these big orange suits, you know, there's a moment that was a little bit difficult and you feel nauseated and not too well. But you know, because of the experience of your colleague who talked to you before the mission, that it doesn't last a long time. The second day, you're always, or let's say 99% of the astronauts, the second day are in great shape already. So you look forward to be in good shape. I have to say that the ascent to space is kind of scary. You can imagine. You are not, you don't have, you are not totally scared, but you are concerned and you are worried because it's a dangerous phase of the mission. Once you're in orbit, it's very safe. The likelihood that you're going to be hit by a meteorite is very low. And you are hit by micrometeorite all the time, but it doesn't matter. But if there's a big one that would make another bad day, and you know the system quite well. The shuttle was very redundant, and if we're losing thrusters or inertial measurement unit or even a computer, it was not a big deal because the vehicle was very redundant. Another relatively dangerous phase was the re-entry. Of course, we lost Columbia in 2003 during the re-entry. But before the Columbia accident, we were not aware of the fact that the reentry was so dangerous. So I was not too concerned about reentry at that time. But the on-orbit phase of the mission is something where you can really work. You have a peaceful mind. You do your work. You focus on your work. You don't have any worries. It's a very serene part of the mission. And of course, the view outside, whether it's above the horizon with the sky or below the horizon with the Earth, is so beautiful that it's really an amazing experience. So to summarize, the ascent is a little scary. The on-orbit phase is wonderful. You just do your work and focus, but it's wonderful. The re-entry, at the time I flew, was not considered too scary, but after the Columbia accident, I must say it was considered a more scary portion of the flight than before.
It all sounds very exciting and worth to try. Maybe a last question now that we're reaching the hour. We have once back on Earth, actually, to follow on this. Did you have any trouble adjusting to life here after your space trips?
Adapting to life on Earth?
Exactly, yes, after coming back.
Well, short term, of course, you land and you are sitting on your seat with your pretty heavy and somewhat rigid orange suits. And I remember that standing up from the sitting position after landing was very hard. So you are so accustomed to weightlessness, even after about 10 days, that was a typical duration of a shuttle mission. Even after 10 days, when you come back at 1G, you feel very heavy. And then we had to crawl all the way to the hatch. And from the hatch, we were getting into a van where there were medical doctors taking care of us medically before we came out of the van and do the walk around the spaceship with all the NASA and ESA officials. But I remember that I had the feeling of coming back to a planet that was different from the one I had left 10 years earlier, with a much more gravity. Of course, we know the gravity was the same, but you are much more sensitive to gravity. And even, lifting the glass of champagne after the medical check following the landing, I remember the glass of champagne was so heavy. And taking pictures also, Nikon F4, which we used at that time, was so heavy. So that's the main effect shortly after landing. After a relatively short mission, like 10 days, I would say the second, third day, you were nearly normal. It was only about 24-hour feeling heavy and having sometimes problem with balance. If you close your eyes, you could not necessarily stand straight. You would fall down because your balance system is not working properly. But second day, third day were fine. After long duration mission, and maybe Alexander Gerst next Thursday can talk more about it, it takes much longer, of course, to recover after a long mission. After a short mission, a few days only, and you are 100%. And right after landing, you feel so heavy.
Yes, physically that's true, but emotionally I would say, or maybe I would imagine that you feel different towards the Earth, like you appreciate it because you saw it from above and
yeah,
you understand it better.
It's an enormous enrichment mentally, and it makes you become aware of a lot of things. It's your awareness level is rising a lot, and it's really an amazing experience. And it's something that you never forget. The views of the Earth from space, like the Earth, like a big spaceship with about 8 billion crew members and no captain.
That's right. Sounds amazing, though. Thank you very much, Claude. With this, I will conclude the session. I would like to thank you once again for sharing your knowledge with us. It's great to see how we have come to understand our universe better thanks to Hubble. And it's really impressive to see all the pictures in the depths of the universe with the galaxies. And we're also grateful actually for your job because you went up there to fix it so we can actually benefit from it. That's really nice of you. Thank you. And yes, for everyone watching, please stay tuned. Tomorrow we have the next student project show at 11 hours Central European Time. We'll have P8 Ampex team presenting. And again, thank you for watching. And don't forget to fill in the survey in the video description below. And have a good afternoon, everyone. See you all tomorrow.
You take care. Bye-bye. Thank you.
Bye.